SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 2 Vapor Power System Part 3. So, in this lecture our main focus would be to discuss about heat absorption concepts in water tube boilers. So, in our last lecture we have exhaustively talked about different components of the water tube boiler. In this lecture we are going to summarize different components such as superheater, attempter, reheater and economizer. So, these 4 components are nothing but a heat exchanger unit and they are being interpreted in different forms. We will see how or under what circumstances or what are the different criteria or what are the different forms in the subsequent part. So, let us revisit which we discussed in our last lecture, that is water tube boiler. So, essentially a water tube boiler has important components like steam drum, superheater, reheater, economizer, air preheater and of course we have headers, downcomers and risers. So, the main aspects of our lecture today that we will be focusing on 3 important parts. One is superheater, reheater and economizer. Of course, steam drum is also the part of it. So, in general the modern steam generators produce the very high pressure. The modern steam power systems or steam generators operate in the pressure range of 70 bar for saturated steam and pressure range of 240 bar for superheated steam. So, they have the steam generator is nothing but the integration of different components like for main integration to furnace, economizers, boiler, superheaters, air reheater and air preheater. So, our main goal in this lecture is that we will be mainly focusing on the superheater part. So, let us see before you go for those superheater component, let us think about in a broad sense what do you mean by heat absorption in the water tube boilers. So, basically our main job is to add heat to the working fluid, in this case is water, and heat addition takes place in a heat exchanger units like economizer which is located in this line, and here if you can see here the economizer is located at the first basic heat exchanger that supplies water to the steam drum, and downcomer and riser circuit gives the saturated steam. Superheater gives the superheated steam, and reheater uses the bypass from the turbine and reheating again in the same steam generation unit. So, essentially speaking, the feed water from high pressure heater enters the economizer where it receives heat from the outgoing fluid gases till saturated liquid stage, then fed to the drum. Then saturated liquid falls through the downcomer circuit into the bottom of the header and moves through the riser circuit where the water is partially boiled back in the drum and saturated steam goes out of the steam drum. Then from there it enters to the superheated steam. Now from the superheated heater unit, it supplies to directly gives to the is fed to the turbine. So essentially speaking, the role of superheater is to keep this dryness fraction to this maximum possible extent, so that there is no water content in the boiler. Now let us think about this water tube boiler in a thermodynamic diagrams. So whatever we have discussed so far, like what happens in the economizer or a boiler, many times this boiler in this unit we also call as a evaporator, then superheater and reheater. So if you look at these thermodynamics TS diagrams, we see that point 1 refers to the liquid phase of water, point number 2 refers to the saturated liquid, point number 3 refers to the saturated vapor, point 4 is saturated superheated vapor, again point 5 is the saturated vapor, and point 6 is the superheated vapor. So what it means is that for a kg of steam, heat is absorbed in the economizer, which is in liquid phase, then evaporator, which is liquid vapor phase or latent heat of vaporization, and then in the superheater heater, that is gas phase. The multi-stage expansion from low pressure turbine involves reheating of steam from saturated state to superheating state in a reheater. So the basic idea is that the reheater concept is also introduced in the steam generator unit of the water tube boiler. Now if you want to calculate the heat absorption in a water tube boiler per kg of steams, and since you know the state points 1, 2, 3, 4, 5 and 6. So using the steam table, you can calculate these enthalpy values, and these enthalpies are values depends on the state point coordinates of 1, 2, 3, 4, 5 and 6. Now once you know the enthalpies, then you can calculate for component wise what is the heat load. So the total heat load is nothing but the addition of all these 4 component loads, and then we can find out what is the percentage share of for economizer, which is evaporator, or we can also, this is also many times many books also refer evaporator as boiler. This boiler because the word evaporator is normally used in the refrigerant systems and where the evaporation of refrigerant takes place, but here again the boiler or evaporation word concept remains same, with a view that it is from steam and water unit. Then we can calculate the superheater load and we can calculate the reheater load. So percentage share can be calculated by knowing their enthalpy values. Now let us focus on the most important component of steam generating unit, that is superheater. So superheater is nothing but a kind of a heat exchanger. So once we get the saturated steam from the steam drum at state point 3, it enters to the superheater. So this is basically from steam drum. Schematically, if you look at this figure, from the steam drum the saturated steam enters at point 1 and superheated steam leaves at point 2. So these are called as superheater coils. That means when it passes through these superheated tubes, it interacts with the flue gases, which is essentially at high temperature Tg1, and by taking heat from the flue gases, the temperature of the steam also further increases. So thereby we also need to find out we also need to do the energy balance for the flue gases and the mass of the steam requirement. So this particular problem can be viewed as a heat exchanger problem, and this heat exchanger is nothing but a counterflow heat exchanger. So in this case, we see that along this length or area, if temperatures are plotted or temperature profiles are done for steam and flue gases, we can see that flue gases temperature falls down from Tg1 to Tg2, and whereas steam temperature increases from Ts1 to Ts2. So, thereby we can model this the superheater tube as a counterflow heat exchangers. Now, let us see what are the different types of arrangements that a superheater can have. Like you have seen those coil superheated tubes. So, they are nothing but three types. One is, that means the heat exchange can take place pure convective mode, pure radiant mode. Pure convective mode means it is called as convective superheater. Pure radiant mode means it is called, they are called as radiant superheater. Pedant type superheater means it is a combined version of convective and radiative mode. So, essentially if you look at this TS diagram, you see here that superheating units operates between state point 1 and 4, because already we have saturated steam that enters at state 1 and we superheated the state 4, the steam leaves. So, through this the heat addition takes place. So, basically if you want to go for very very degrees of superheated is very high, then we have to go for radiant type, or if your degree of superheated is less, that means somewhere you want to stop this superheating at point 2, then convective superheating heater is sufficient. But in some cases we also require both type. What does this mean? That means it has been shown that, but one important thing is that while increasing the steam temperatures, we must see that there is a characteristics that when the steam flow rate increases or the mass flow rate of the steam increases, and this increase with increase in the steam flow rate, the outlet temperature, if you are using the convective superheater, this outlet temperature characteristics curve is in a increasing trend. Whereas, if you use radiant superheater, the with increase in the steam flow rate, the outlet temperature drops, but this is not the essentially the user requirement. So, user wants a flat curve, like for the range of operation, let us say 40 to 80% of steam flow rate, you need to have a flat type of curve, whereas the temperature remains has to be flat. So, for that case the combined superheaters are most beneficial, and they are called pedant type superheaters. So, that is the main advantage. So, like if you see this type of configurations, a pedant type superheaters is like a vertical inverted tube, and this gas flow comes. So, in partially it is the mode of heat transfer is partially convective and partially radiative. That means, initial version it is convective, and once it is already superheated to some extent, it has to be operated in a radiant mode. Whereas, in a purely horizontal type superheater, which is mainly operates in a convection mode. So, this is how the configurations of superheated heaters are required for the application of or increasing the temperature of steam. Now, whatever I have explained, if I have to read out, then we can say that heat absorption techniques in the superheaters can be listed as follows. So, they are classified as convective, radiative or combined mode. Heat is taken from gas to the steam. Convective modes are normally located in the convective zone of the furnace. That means, in the entire steam generator unit, it is mainly closer or just ahead of the economizer. And so, these convective superheaters are normally referred as primary superheaters, where the saturated steam is from the drum is admitted. Now, after convective superheating, the stream proceeds towards the radiant superheater, which is placed in the radiant zone of the furnace. So, radiant zone means this means it is close to the wall of the furnace. so as to absorb the heat only by radiations. Now, steam leaving from radiant superheater goes to de-superheater, where it is highly pure water is spread to the steam at a desired quantity, such that last stage of superheating or combined mode is normally done. So, that is called as pedant type superheaters. So, this spraying is again required for the controlling of steam, and I will come back to this point at the later stage of this lectures, why it is required, why this spraying of water is required in a pedant type superheaters. And this normally this pedant type superheater is called as secondary superheaters. So, at the end of the superheating units, the constant flow rate of steam should go at a fixed temperature. So, that is the essential requirement when the steam enters into the turbine. Now, let us give more view to this convective superheating concept, where heat transfer is mainly convections, and this is the most simplest type of mode in which heat exchange can takes place. So, I have already mentioned the heat is taken from the flue gas, thereby flue gas temperature drops and steam temperature increases from Ts1 to Ts2. Now, coming back to heat exchange or bit for this superheating heaters, one can model it as a heat exchanger model. First thing, one can find out the convective superheating from these equations, how much heat is being added during the convection superheating from 1 to 2, that can be calculated as the mass of the steam into enthalpy difference, that is H2 minus H1, and that is equal to the energy that is lost by the flue gases, and this flue gas is normally modeled as a m times Cp delta T. So, Cp is the specific heat of the flue gases, mg that is mass flow rate of the flue gases, Tg1 and Tg2 the temperatures at the inlet and the exit of the superheater. This is one aspect. Now, with respect to superheated heater unit, this can be modeled that QCSH can be equal to U0 times A0 delta T LMTD. So, LMTD is nothing but the logarithm mean temperature difference, and that is we refer for a counter flow heat exchanger using this figure. So, LMTD is defined by delta Ti, and delta Ti occurs at this one unit, and delta T is the exit. So, at the inlet it is Tg1 minus Ts2, and at the exit it is Tg2 minus Ts1. So, knowing this delta Ti and delta Te, we can calculate this logarithmic mean temperature difference by this expressions. Now, what is U0? U0 is the overall heat transfer coefficient, and this overall heat transfer coefficient is related to the convective heat transfer coefficient and its thermal conductivity and convective heat transfer coefficient for outer wall and for inner wall, and this is the along the thickness. So, essentially these are nothing but the resistance offered for this heat exchange to happen. So, now once you know U0, you can find out, knowing this convective heat transfer coefficients at the inlet and the outer surface, inlet surface and outer surface of the tube, and along this conduction takes place in the along the thickness of the tube. So, basically if you can say this is your thickness of the tube, and here this is inner part and this is outer part of the tube, and essentially this is your inner diameter and this is your thickness, that is xw. So, for this expression you find Hi, which is inner convective heat transfer coefficient at the inner wall, Ho is the convective heat transfer coefficient at the outer wall, and within this thickness the conduction takes place. So, basically here we have flue gases here we have steam. So, heat transfer takes place from flue gases to steam. So, thereby you can model this as a convective mode at the outer surface, convective mode at the inner surface of the tube, and then along this thickness it is a conduction mode of heat transfer. So, this then and for the outer surface and if how many, what is the size of this A0, that means what is the size of the tube, that can be called as outer surface area of the tube, that is nothing but number of tubes into pi d0 into L, that is surface area, that is outer diameter of the tube. And of course, mass flow rate of the steam can be calculated by number of tubes into pi by 4 di square into Vs into Vs is the velocity of the steam, small Vs is the specific volume of the steam at that condition. So, most of the data will be given to us, and accordingly we can use these equations to design the heat exchanger. To design the heat exchanger means you need to calculate the what is the area requirement, what is the outer diameter, what is the number of tubes required, all these parameters. Now, another same philosophy can be extended for radiant superheater type, but there for radiant superheater we have to use this equation for radiations, that is sigma A T times Fw Tf to the power 4 minus Tw to the power 4. So, this is the radiation heating, and using these equations that can be correlated with respect to what is the rise during from the point 2 to 3, because 2 to 3 normally we use radiant superheater. And this radiant superheater means that the steam is allowed to see the surface of the wall, that means at the wall the radiation is most predominant. So, the steam is allowed to be exposed to the wall side. So, that is the reason the radiant superheaters are located in the radiant zone of the furnace, that provides greater heat absorption by radiative mode of heat transfer. So, in other words, for a higher degree of superheat, we require that the steam should be exposed to the high temperatures to view the combustion flames. Then moving further, we can say there are, of course, there is another limitations to it, that for radiant superheater your velocity to get the maximum benefit of radiation mode of heat transfer, the steam velocity should not exceed 7.5 meter per second, and their heat transfer coefficients are 3.14 kilowatt meter square with maximum heat flux of 116 kilowatt per meter square, and this flame temperature is almost independent of load. So, as the steam flow increases, the heat transfer per unit mass flow rate is decreases. So, this is the characteristics curve. When you increase the steam flow rate, the outlet temperature drops. So, this is the biggest disadvantage for a radiation mode of heat transfer. So, basically a most appropriate choice is to use the combination mode, that is convective and radiative mode of superheaters, and such superheaters are known as pedant type superheaters. So, in a pedant type superheater, that means normally it is in the region of 3 to 4. When you go for higher degrees of superheating, we see that pedant superheaters, they are like inverted U tubes exposed to the gas flow. So, and if you see this thermodynamic diagram, the gas temperature, flue gas temperature drops from Tg1 to Tg2, but if you look at the steam side, so steam side it is from Tst1 to Tst2, it goes as a convective mode, and here a counter flow type of steam enters, so that the curve is little deviated from this actual rise. So, basically speaking, we are going to going to mix these two type of streams in a such a way, so as to require the flat curve. So, how we are going to do that, I will come back in the subsequent slides. So, that is the most that is what normally is done to control the temperature at the outlet of the superheaters, and we need to have essentially get a flat curve, that is flat steam outlet temperatures, which is insensitive to the load change. So, basically pedant type superheaters, we can say 3/4 heating is made as a counter flow, 1/4 heating is considered as a parallel flow. So, this side we say it is a counter flow, and from this side we say it is a parallel flow. So, if you look at steam and gas point of view, from this side it is a parallel flow, from this side it is a counter flow, and this is the most economical arrangement operations for safe operation of the thermal failure of the materials. And this is what I was emphasizing, how do you get this combined superheater, pedant type superheater in a flat curve. So, that is what we call this as a process, which is called as attemperation. So, in certain case we require the convective and radiant superheaters are arranged in series to yield a flat final curve over final temperature curve over a wide range of temperatures. So, attemperation is a method of a reduction of steam temperature, that is done by two methods, one is surface attempter, other is the spray or direct contact type attempter. Now, the surface attempter is nothing but a cell and tube type of heat exchanger. So, what happens here is like this. So, if you look at conceptually, this is your steam drum, and from this steam drum the steam comes out, saturated steam comes out and enters to this superheated zone, and the superheated zones are two types, primary and secondary. Primary is normally made as convective type and secondary is made of radiant type, not exactly radiant, pedant types. So, basically pedant type combines radiant and convective mode, which is partly counter flow and partly parallel flow. Now, if you look at this curve, in one case in a convective superheating mode, that is in the primary, the outlet temperature increases with increase in the steam flow rate, but in the radiant mode outlet temperature drops. But in to have this flat curve, we need to do the pedant type superheaters. But then what happens? Controlling the temperature becomes vital, because these two are very huge temperature difference. So, for that reason what we normally do, that between primary and secondary superheater, that is a primary superheater, it gives a steam temperature of this range, and secondary superheater that is the final requirement, let us say 550 degree centigrade need to achieve. Now, in between, now if you do not use this attempter, then what may happen is that this the curve will keep on increasing after 550. That means 550 is the point A, that is landmark point. So, beyond that the temperature should not go, but as and continuously with increasing the load rate also, this should remain flat at this point. And for that reasons we use the surface attempter or direct contact type attempter to bring back this flat curve. So, how do you do? We do by a method called as spray attempter cooling, where some collected water from the steam drum is being sprayed, so that to keep this thing in a flat curve, so that unnecessarily the temperature should not rise, rather it should lead to a flat curve. And the amount of this flatness we can control by controlling the addition of the mass water or water spring mass into the main steam. So, and this is again another unit called as a cell and tube heat exchanger that collects the steam from the pedant type superheater and regulates the temperature for a flat curve, and this temperature is achieved by controlling the diverted steam. So, what is done is some portion of the steam from the primary or secondary superheater is diverted to cell and tube heat exchanger that contains boiler water in the cell. So, the steam gives up some heat to the water and then the remixes to the primary stream upon entering into the secondary heater. So, basically primary and secondary, between primary secondary heating we give a kind of a heat spray cooling, so that the temperature of the temperature of the entire unit does not go beyond the point A. And again what we have the location of this attemptator means basically attemptator can be either side, either type like surface or spray or direct contact type. They can be located before primary superheater, after secondary superheater, or in between primary and secondary superheater. So, this is the three locations this attemptator can be used. So, the first choice is first choice is means if it is used before means it can lead to the condensation of saturated steam on the boiler surface before it enters the condenser. Last choice means it is used in the after superheater, then controlling the steam temperature exceeds the final desired value. So, if you look at after here, already it has crossed. So, then the best way is that before it leaves the superheater, entire temperature control has to be done in such a way that the curve relatively remains flat. So, this is what we say spray cooling or type of attemptator. But there are another way of doing this similar practice is through gas recirculations. So, many times what happens, the gas recirculation is used, in which gas from some point downstream of the economizer outlet is recirculated back to the furnace by a fan. So, by doing this we call this as a gas tempering. So, essentially this also does, this cooling can happen by a gas mode from the economizer unit, and that process is called gas tempering. Okay. Now, let us think about a most effective way of attemptation, that is the second method, in which we call it as a spray or direct type attemptator, where we can reduce the steam temperature by spraying the low temperature water from the boiler or economizer exhaust in the line between primary and secondary superheaters. So, what happens is here there is a steam flow, and there is steam flow comes from the primary superheater and it enters to the secondary superheater, that is MS plus MW, and relatively if you can say that this line, this mass flow rate has to follow this flat curve, which essentially means that we must regulate how much water needs to be sprayed, and this arrangement is done through a spray nozzle. So, this spray nozzle arrangement configuration is a Venturi type nozzles, and in which water is sprayed through this Venturi type nozzle, of course steam along this steam path. So, along this steam path, when this steam comes and it interacts with the water, its temperature drops. So, when the temperature drops, the final number, that is final value, which is MS plus MW, which we get, that is the essential requirement of load, and for that load the temperature is obtained as a relatively flat curve, and typically the temperature requirement is about 550 degrees centigrades after superheating unit, and most of the cases, and this depending on the requirement, we can control how much mass flow rate needs to be added. So, more or less this has been seen to be a most effective way and most rapid and sensitive means of temperature control in a steam generator. Then a simple energy balance equations can be applied, because you see here that referring to this figure, steam flow rate is MS, and when it enters at enthalpy let us say HS1, and mass of the water which enters from the let us say steam drum, it is MW. At that pressure we can have this enthalpy value, that is HW. Then the total mass that goes out is MS plus MW, but at an enthalpy HS1. So, essentially speaking, from this point to this point there is drop in temperature and pressure remains same. So, to maintain the pressure to be same at entry point, relatively this we have similar pressures from this water inflow and the steam inflow. So, if there is no involvement of work, heat and changes in the kinetic or potential energy, then you can simply frame the energy balance equations, that is MH HS1 plus MW dot HW is equal to MS dot plus MW dot HS2. Okay. So, this is what the attemptation is required for a superheating unit to generate a flat curve. So, with this viewpoint, let us see some numerical problems that can be attempted in the topic of superheater attemptator, and of course, the heat loads on the water tube boiler. So, the first problem talks about a modern steam generator unit in which superheater coil has to be incorporated. Its dimensions are given, like internal diameter 52 mm and thickness 5 mm. Exit condition of the steams are as follows, that means steam exit conditions are 60 bar and 500 degree centigrades, flow velocity 15 meter per second, mass flow rate 75 kg per second. Due to material restrictions, in the heat flux the coil should not exceed 150 kilowatt per meter square. So, what is the idea is that if we have no information about the flue gas, we have only information about the superheater coil. So, basically this is the superheated coil. The steam enters at point 1, it is called saturated vapor, which enters from the steam drum and the steam exit conditions in the superheated coil is superheated vapor and that is state 2 60 bar 500 degree centigrade, and it enters through these tubes in a continuous manner, and this side we have flue gases of mg dot Tg1 and flue gases leaves mg dot and Tg2. That means, heat is taken from flue gases to this steam, and essentially speaking it is a convective type of superheating, where we can draw this curve. We are at the point 1, steam requirement is at point 2, and this heat in a temperature entropy diagram, this heat we called as QSH, superheated load, and this QSH is to be supplied by Q dot flue gases. Of course, no information about the flue gases in these things. So, we do not need to bother about this flue gas as of now for this problem, but what is needs to be done is that we need to find out what is the heat load, and from the heat load we need to find out what is the number of coils or length of the each coil. So, the solution has to start, you have to keep steam table intact. So, using the steam table, what we can find out at state 1. So, at state 1 we say it is saturated vapor. At 60 bar at this point. So, this will give you H1 as Hg. So, you have to refer saturated vapor water table, and this value will be 2784.3 kilojoule per kg, and state 2, which is normally at this point, it is superheated vapor, and that coordinate is 60 bar 500 degree centigrade. So, superheated table will give you H2 as 3422.2 kilojoule per kg. Of course, we require specific volume, please note down that. So, that number is 0.05665 meter cube per kg. Then you also know mass flow rate, that is of the steam, that is 75 kg per second. Then you can find out what is QSS, that is m dot s into H2 minus H1. By inserting the value, we arrive at it is 47842 kilowatt. But we see that this is the material heat flux on the coil should not exceed, that means kilowatt per meter square. So, accordingly we must find out the area, surface area of coil. So, that is A 0, that has to be total, that is QSH divided by 150 kilowatt per meter square. So, this number becomes 319 meter square. So, once you know the area, then we also require some information, we also require the mass flow rate. So, from the mass flow rate we can calculate, from the mass flow rate equation, which is nothing but A2 V2 by A2 area into velocity divided by specific volume, and that mass flow rate value is given 75, and A2 is nothing but number of tubes n into pi by 4 d I square, and V2 is equal to 15 meter per second, and di is given as 52 mm, that is 0.052 meter, and we also know small v2 specific volume is known. So, by putting this value we can say n times pi by 4 di square is equal to m dot s into V2 by V2, and from this equation we can calculate what is N. By inserting this value we can calculate N as 134, that is number of turns in the coil for which heat flux should not exceed as 150 kilowatt per meter square should be 134. Then this A0 surface area, A0 can be written as N into pi by 4 pi d0 into pi into d0 outer diameter into length. Now, here outer diameter of this tube can be calculated as inner diameter plus 2t. So, if you look at this tube, this is your thickness, this is your di, and this is t, and this is do. So, d0 would be di plus 2t. So, this becomes d0 is 52 plus 5 plus 5. So, this is 62 mm. Now, putting in this equation, so we can calculate that L is equal to A0 divided by N times pi into d0. So, we have A0 as 319 meter square, N is 134, d0 is 62 mm. So, putting this value we can say L is equal to approximately 12 meter. So, basically this is asked what is the number of coil, that is 134, length of each coil it is 12 meter. Now, next question is about the spray attempter which regulates the flat curve for the superheated unit. So, what does this, if you refer this figure, we have this side we have secondary superheater and this side we have primary superheater. To regulate this flat curve, we, or it is a like this is a flat curve, we have a spray attempter for temperature control of the steam. So, basically speaking, what we see is steam enters the attempter at 180 bar 500 degree 520 degree centigrade, that is m dot s enters at 180 bar 520 degree centigrade, and spray water comes from the drum at m dot w comes from the drum, that is about 190 bar. So, more or less these two temperatures are similar because they have to come out at same pressure of 180 bar, and but temperature has to drop down 480 degree centigrades. So, to control this 480 degree centigrades, we are adding water into this through this Venturi type attempter. So, basically we also require steam table to find like inlet, steam inlet which is 180 bar and 520 degree centigrade. So, this will give you HS1 as 3378 kilojoule per kg, steam outlet that is 180 bar and 480 degree centigrade. So, this will give you HS2 requirement as 3203.2 kilojoule per kg, and inlet, water inlet, that is saturated water at 190 bar. So, saturated pressure table can be referred to find out HW or HF is equal to HW at 190 bar. This number is 1776.5 kilojoule per kg. Now, we also know that per kg unit mass of the steam, that means m dot s is equal to 1 kg per second. So, the working equation is the energy balance that is m dot s HS1 plus m dot w HW is equal to m dot s plus mw into HS2. So, so this equation we can simplify as dividing by ms. So, we say it is HS1 is 3378 plus mw by ms into HW. HW is 1776.5 is equal to 1 plus mw by m dot s into HS2. HS2 is 3203.2. So, by solving we can say mw by m dot s is equal to 174.8 divided by 1426.7 and this number is 0.122. So, in other words we say mass of the spray water requirement per kg of steam is 0.122 kg per second, and this mass must be required to regulate the steam temperature to be maintained at 480 degree centigrades. And last problem is a very simple problem, which this problem is dealt with heat absorption concept for a modern steam generator. So, what the problem statement says is that we need to estimate the heat loads for modern steam generator, that involves an economizer, that involves a boiler or evaporator unit, that involves a superheater, and of course, we also have a reheater unit. So, basically steam which is at liquid state enters into the generator unit in an economizer. It goes up to state point 2, which is the saturated liquid at point 2. Then at same pressure the steam leaves at the evaporator or boiler at state point 3, and this heat transfer is mainly latent heat, and from 3 to 4 it is the superheating heater unit, and again from 5 to, and after expansion process in the turbine the reheater unit dominates here. So, from 5 to 6 and it goes to state 6. So, basically we have the state point requirement, and for each state point we need to calculate this enthalpy coordinates, and for each of the enthalpy coordinates once we find out, we can equally calculate the what is the heat load share. So, for this again suggested to use steam table. So, state 1 which is liquid water 45 degree centigrade. So, for this liquid water, referring to the saturated liquid value, we can say H1 as 188.45 kilojoule per kg, and state 2 is saturated liquid enters into the boiler or evaporator at 8 megapascal. This is saturated liquid 8 megapascal. So, saturated liquid table will give you H2 as HF value at this pressure, that is 1316.6 kilojoule per kg. State 3 is saturated vapor at again at same pressure 8 megapascal. So, here it is latent heat of rejection or latent heat of addition. So, H3 is equal to at same pressure we say Hg. Hg value is 2758 kilojoule per kg. State 4 is superheated vapor, that is at 8 megapascal and 480 degree centigrade. So, H4. So, H4 value is 3348.4 and state 5 is saturated liquid after entry from the high pressure turbine. So, that is at 0.7 megapascal saturated vapor. So, H5 2763.5. So, state 6 reheater. So, reheater is operating at same pressure superheated vapor at 0.7 megapascal and 440 degree centigrade. So, this will implies H6 is equal to 3353.3 kilojoule per kg. Now, we have all the state point enthalpy values. We can find out for case 1 economizer Q EC is equal to H2 minus H1. So, this value is 1128.15 kilojoule per kg. Then we have boiler or sometimes is called as evaporator. Q evaporator is equal to H3 minus H2. So, this value is 1441.5 kilojoule per kg. Then superheater, Q superheater is equal to H4 minus H3. So, this number is 590.4 kilojoule per kg. Reheater, Q reheater is H6 minus H5. So, this value is 589.9 kilojoule per kg. So, adding these 4 we can say Q total. Also we can calculate, that is H4 minus H1 plus H6 minus H5. So, this number is 3449.95 kilojoule per kg. So, we have all the state point values. So, we can find out percentage share, that is Q economizer by Q. That number is 1128.15 divided by 3749.95. So, this is 30%. Similarly, Q evaporator by Q, this value would be 38%. Q superheater divided by Q, this is 16%, and Q reheater by Q is 16%. So, basically speaking, this is the heat load distributions across different components of a steam generator unit. So, with this I conclude this lecture for today. Thank you for your attention.